Hello everyone!
Hi.
Welcome to Gen Z Scholars. My name is Kiam,
And my name is Amy.
and today we will be going over Unit 1, Lesson 2 of AP Chemistry, Mass Spectra of Elements.
It used to be called mass spectroscopy of elements, but whatever. Same material, just different names.
Let's start with some simple facts you need to know for this lesson concerning isotopes.
It's rewind time.
In our last video on Lesson 1 of Unit 1, we went over the concepts of moles and molar mass and how they relate to each other.
In this video, we will learn about isotopes, which are used to find the molar mass of an element.
To start off, each element can have multiple different forms as an atom, isotope, ion, or molecule. So to differentiate and label individual elements, we consider the number of protons in each element.
Protons are the positive subatomic particles in an atom, P for positive. Similarly, atoms also contain neutrons, the neutral subatomic particles, N for neutral. And lastly, electrons are negative subatomic particles. More on atomic structure in Lesson 6 of this unit, but for now, back to this lesson.
The number of protons corresponds to its atomic number on the periodic table. For example, carbon has 6 protons, so its atomic number is 6, and it comes 6th on the periodic table.
All atoms have the same number of protons and electrons. However, the number of neutrons can change.
When there are forms of an atom of an element that have different numbers of neutrons, we call these forms isotopes. For example, carbon-12 and carbon-14 are both isotopes of carbon. The numbers 12 and 14 indicate the mass of the element.
That's probably weird because we're supposed to already have the molar mass as the mass. However, neutrons have mass too, so their mass will change the mass of an atom.
But don't worry, you will still be using the regular molar masses of elements for standard calculations on exams and homework and such, of course unless told otherwise.
Moving on, since carbon-12 and carbon-14 are both carbon isotopes, we know that they must have 6 protons because the atomic number of carbon is 6, as per the periodic table.
All isotope forms of an element are also atoms. This means that they have the same number of electrons as protons. So we know that both carbon-12 and carbon-14 have 6 electrons each, since they both have 6 protons each.
Now for the neutrons, the defining part of the isotope. Whenever finding neutrons of an isotope, just remember man. The mass number of an element minus the atomic number equals the number of neutrons. So, for carbon-12, 12 minus 6 equals 6, so it has 6 neutrons.
And for carbon-14, 14 minus 6 equals 8, so it has 8 neutrons.
Isotopes have different physical and chemical properties, so we use them for many different things. Some are used in medicine to diagnose and treat certain medical conditions. Others are used as culinary preservatives, or to date fossils, and so much more.
Isotopes also have one more very important purpose. They help us to find the molar mass of an element.
This is done through mass spectrometry.
Mass spectrometry is the application of spectroscopy. While these terms are used interchangeably by many, there are differences in their usage and relevance.
Spectroscopy will be gone over in depth during Lesson 6 of this unit. For now, all you need to know is that it is the study of the absorption characteristics of matter.
Spectrometry is the actual measurement of these characteristics and interactions between radiation and matter. It is due to spectrometry that we can get quantifiable numerical results.
But what does all this radiation light and absorptivity stuff have to do with isotopes and masses of elements?
Well, mass spectrometers work by vaporizing substances and then shooting electrons at them to create ions. These ions are then separated by their mass-to-charge ratio. This mass-to-charge ratio is represented by the abbreviation m/z, which you may see on the x-axis of mass spectrum graphs on the AP exam or just regularly in chemistry.
Great. But what does this have to do with isotopes and masses of elements?
Oh yeah, I forgot about that. Basically, since all isotopes have different masses due to their change in neutron number, mass spectrometers can easily distinguish between, separate, and find the masses of these isotopes. Then, once quantified, we can see the relative abundances of these isotopes, which, by the way, you will usually see on the y-axis on mass spectrum graphs. This all comes together to produce the mass spectrum of an element.
And to summarize, the mass spectrum of an element is basically data collected from these mass spectrometry experiments that indicates the patterns and intensities of mass to charge ratios of the ions, or in this case, the isotopes.
Right, and from that, after a few calculations, we can get the weighted average mass of all the isotopes of an element, which we call the molar mass of an element.
Perfect. Now it's time for some practice problems. We will do this first one with you. After, you will be given more to do on your own. Answers and explanations will be provided at the end of this video. Wow, this is such an amazing graph.
I know, right? I wonder who made it. Anyway, onto the actual problem. This beautiful graph shows the mass spectra of an element, X. Using this graph, we will answer the following. First question is to find the molar mass of element X.
When solving problems with percents, it is helpful to convert the percentages to decimals. To do this, just divide the percent by 100. In this case, 95% would become 0.95, and 5% would become 0.05. Multiply each of these decimals by the corresponding atomic mass of the isotope. In this case, we would multiply 12 by 0.95 and 13 by 0.05 to get 11.4 and 0.65 respectively. Adding those two values together will give the average atomic mass of element X, which is 12.05.
The second question asks us to identify this element. To do this, go to your periodic table and find the element whose molar mass is closest to the value that you got. It'll almost never be an exact or perfect value. Just choose the closest one.
If you come across a question where your calculated answer is right between two elements and you're unsure, go back to the graph.
Then, find the highest mass to charge ratio or peak. Out of the two elements closest to your calculated answer, you would choose the one closest to that high peak. But back to identifying element X. In this problem, the highest peak is 12.
Surprise, surprise, it's carbon.
The third question asks us to calculate the percent error. The percent error formula won't be on your reference table, so you will unfortunately have to remember this one. The formula is as follows. Percent error equals m minus t over t times 100, where m is your measured value and t is your theoretical value.
The theoretical value of carbon is 12.011 atomic mass units, or AMU, whereas our measured value is 12.05 atomic mass units. Plug this into our formula and we get approximately 0.325% error.
Just so you know, any percent error of 5% or below is acceptable when conducting a laboratory experiment, which you will also unfortunately have to do throughout the year. Now let's see if you have been paying attention. Question 1a. How many protons does cobalt-60 have? Question 1b. How many electrons does cobalt-60 have? And question 1c. How many neutrons does cobalt-60 have? Question 2. The following graphs represent possible mass spectra of sulfur. Which is the best and most accurate representation of sulfur and why? You can pause the video now and try to answer these questions on your own. Answers and explanations will be given in just a moment. The first question asks about cobalt-60 and its subatomic particles. First, we are asked for its number of protons. Recall that protons correspond to atomic number, which is given on the periodic table. Looking at the periodic table, you will see that cobalt's atomic number is 27, so it has 27 protons. Second, we are asked for the number of electrons. Recall that isotopes are atoms, and atoms contain the same number of protons as electrons. Since cobalt-60 has 27 protons, it has 27 electrons as well. Thirdly, we are asked for its number of neutrons. Recall the Mann equation from the lesson. Mass number minus atomic number equals neutron number. 60 is the mass number, as seen above, and 27 is the atomic number, as seen in the periodic table, which we used earlier. Now just plug in the numbers. 60 minus 27, which gives us 33, so cobalt-60 has 33 neutrons. On to the next question. Question 2 asks about the mass spectra of sulfur. Recall that the ultimate goal of mass spectrometry in this context is to find the molar mass of an element. This means that the first thing you're going to do is find the molar mass of sulfur. Looking at the periodic table, you will see that it's 32.07 grams per mole. Now what you could do is perform all the calculations and figure out the molar mass that each mass spectrum graph gives. Or you could save time and be a cool kid. Looking at all these graphs, you will find a bit in common. First, they all have really easy numbers. And secondly, the bars are between 32 and 33. Now, just by looking at graph A, not even doing the math, you can see that the molar mass it shows is really close to 33. Almost exactly 33, actually. Graph B shows a 50-50 ratio, so simply 32.5. And graph C shows that it's really close to 32, almost exactly 32 even. Now you can look at the molar mass of sulfur again, 32.07. Out of 33, 32.5, and 32, the molar mass of sulfur is closest to 32. This means that the graph that most accurately represents the mass spectrum of sulfur is graph C.